Hi all, and welcome to the Medical AI Lab Reading Group session. Every Thursday, a lab member covers a recent paper in either core AI or medical AI. These sessions are targeted to be broadly interesting to those interested in cutting-edge AI and its applications in medicine. This week, we will have Sameer Sundrani presenting the paper, Oscar, Object-Semantics Aligned Pre-training for VisionLanguage Tasks. Without further ado, I'd like to welcome Sameer to share this paper with us.
Yeah, it's great to meet everyone. So my name is Sameer, like Brenham said, and I'm a senior majoring in biomedical computation at Stanford. Today, I'm pretty excited. This paper is really interesting, and it's called Oscar, which stands in some parts for Objects, Semantics, Aligned Pre-training for Visual Language Tasks. And it came out of the GAG group at Microsoft Research a couple years ago and presented at the European Conference on Computer Vision. And let's get started. So I'll tell a little bit of an outline before we get started. So I'm going to talk a little bit about background in vision and language tasks and focusing pretty generally on what that means for the vision language community. And then I'll talk about the main contribution of Oscar and sort of what the big acronym means and what their real contribution was to the field. And then their fine-tuning experiments and corresponding results. And maybe throughout the time, if there's any questions or anything, feel free to interrupt me, or we can wait till the end. Either way works. So for background, we start with what exactly do we mean by vision language tasks? What do we do with them? What can we do with them? And so really it's about aligning or asking questions about an image and corresponding text. So for example, there's a number of things we can ask about, say this picture of a dog sitting on a couch. Can we identify what's in the image? Can we map those things to a caption, say a dog is sitting on a couch? Can we ask questions, is a cat sitting on a couch? Is a dog sitting on a couch, etc. So image text retrieval is really about mapping corresponding text or image and sort of messing up the text or the image and saying, asking a binary classifier, are these images and text paired together? And you can use a number of data sets. You can use a COCO data set or whatever you want, but that's the general task. Another task may be asking a caption or to create a caption on an image. So I could just provide this visual representation of a dog sitting on a couch and ask my model to output a caption, a dog is sitting on a couch. Or I can input a novel image, something that wasn't seen in a training data set. A classical example of this is this man in sunglasses sitting on a couch with an accordion, and ask your model to output an image for something like an accordion or a caption for an accordion, but you've never seen the accordion in your training. And so that's a classic task. Another couple tasks are answering questions, more complicated questions or simpler questions via VQA, which is visual question answering, and GQA, which came out of Stanford pretty recently. But you sort of have a multiple choice task to answer a question about an image. So that'd be VQA. And GQA would be something like 1,800 or so different answer choices, and you have to choose maybe via softmax the best one. And finally, natural language reasoning is just sort of asking a Boolean question about an image. Is it true that a dog is sitting on a couch? And you want to output a yes or no with some probability that is your claim true or false. And so the vision language community has done a number of things in the past, but mostly it's focused on taking visual representations and embedding those things to a vector called V. And there could be a number of visual features or regions of an image. And then word embedding, so tokenizing words and then embedding them in semantic space to a vector W. And really in the past, before Oscar came out, the idea was to concatenate these two things together in a tuple, or just literally concatenating them, and input the concatenation at VW or WV, where W is the word embeddings and V are the visual region features, to a multi-layer transformer, similar to the Raswani papers and BERT, for example, to learn some sort of semantic alignment. But the issue is, before this paper actually, there's sort of a challenge between separating various images and features in the image from each other. So for example, in the visual feature space, one could see, because in 3D space, a dog could be sitting on top of the couch could be behind the dog, and for a number of reasons, these things actually align or are very close to each other and don't separate very well. So when looking at the visual features, they're quite close together, where the couch is the orange triangle and the dog is the red square. These things are sort of ambiguously separable. We don't know where the difference is. However, in terms of the word embedding in semantic space, they're actually quite different and they're easily separable. And so that's something we want in to learn and also just want in general. So that's the first issue. The second issue is, while we may be able to produce a caption or something like that for an image for this dog sitting on a couch, we don't really have an explicit alignment between the actual objects in the image, such as dog and couch, to the outputted caption. So while we could align, say, this image and text together, we don't really have an explicit labeling that this image has a dog and a couch in it. And so that's what this Oscar paper actually, and the authors introduce. And their main contribution and their key idea is to use these tags, the actual objects in the images, as anchors for pre-training. And so most papers in the vision language community focus on pre-training and then fine-tuning later on for a particular task, like the tasks I already mentioned, but they don't include an object anchor. And so the main idea here was, you can take something like a faster arse convolutional net, and instead of just getting the visual feature representations, we can also get an object tag, call them Q. And instead of inputting the word and visual features together, we input a word tag image triple into our model. And we don't really change a lot about the model itself. It's really just the same multi-layer transformer with self-attention. But now the input adds this anchoring, which is, if we keep the running example as a dog on a couch, we input dog and couch as our sort of tags to sort of anchor us between visual space and the actual word space. And while it may seem like a simple idea, it actually works quite well. And so before I get into the results, I want to talk about exactly what they did in their pre-training routine. So they think about this in terms of two views. And I think the anchor is a good sort of way to picture this. You have a modality view, which is sort of, you have an image and a series of words, the caption. And one of these things come from the image and the other one come from words. And in some way, we want to align them together. But we also have these tags, which come from the image too. But we want to, in some way, train them to become closer together. And so when we view these as coming from different modalities, so we say, okay, we have these tags that come from the visual space, but they are words. And we have the actual region features of the image, which come directly from the images. We want in some way to make these things come close together. And so what they do is they implement a contrastive loss across these tags and region features. And so they basically just randomly sample these pairs of region and object tags and mess up one of the tags. They'll input it from a random sample of all their corpus of tags and use a binary classifier on top of the multi-layer transformer. So they really just add a projection layer on top at the very end of the transformer to binary classify whether or not this object tag and region pair come from, should they be paired together. Then they combine this with a dictionary view, which is taking a completely different approach to thinking about the loss. So instead of separating where the vectors are coming from, we separate what type of vector they are. So for example, object tags, while they come from an image, could also just be viewed as words themselves and operate in the semantic word space. And so we should be able to match those two close together. And so they use something similar to the BERT pre-training task, where they take these word tokens, including the object tags, and just concatenate them and then place a mask over a random word or words in the sequence of words, and then ask the model to predict that masked word. And so both of these losses are a negative log loss, and they just add them together to get their pre-training objective and train accordingly. And with this, they they basically pre-train and then fine-tune over a number of tasks and then see across all these various tasks, how well does this pre-training look? And I should note here that they make a very clear point that they could have used more complicated loss metrics, and many papers before this actually do, but they really wanted to focus on this idea of separating the difference between modality and trying to see if we can align them in a simple way, in some ways an intuitive way, together. So if there are no questions on this sort of two different views and alternative ideas, their experiments are actually quite interesting, and what they show is very cool. So let's get to what they fine-tuned on. And they literally fine-tuned on exactly the same tasks that I mentioned beforehand. So those are image text retrieval, captioning, novel object captioning, answering questions, and natural language reasoning. And they compare against three different types of state-of-the-art. So they use a state-of-the-art with a smaller model, one that's not based on a multi-layer transformer, one that's about the size of BERT base, and one that's about the size of BERT large. And the only one here that's about the size of BERT large is something like the Uniter model that came out just before this paper. And they basically fine-tune for each one of these tasks separately. And I'm not going to go into the details on their fine-tuning for this task, because this wasn't really the point of the paper. The point of the paper was really the anchoring in pre-training routine. But with that anchoring, they show that their model, Oscar, both the BERT size, BERT base size, as well as the BERT large size, achieves across the board, except for in the GQA, state-of-the-art. And all the blues here are state-of-the-art performances on their metrics. And if everyone can see the little delta at the bottom, you see the relative increase in performance across each one of these tasks. And so for image retrieval, text retrieval, image captioning, etc., we see some ranging from a small improvement, say to novel object captioning, to a quite large improvement in something like image captioning, where Oscar now beats the prior state-of-the-art by quite a lot. And so they go into far more detail into their specific experiments for each one of the tasks, but these are sort of a summary of what they did and sort of how Oscar compares across the board. I'd suggest if you want to look at more details, check out the table 2 in the actual paper, and I have the paper link at the end. But it's quite remarkable, and it was really, really interesting to see just something simple as an anchor could help out for these fine-tuning tasks later on. But they also do a couple of qualitative things, and one of the things they do is say, how close can we get these image and text alignments together? And so they use this stochastic neighboring embedding 2D visualizations, and which is pretty common. And I want to start on the right side here. So just for some explanation, the pluses are the image representation in 2D, and the circles are the text representation in 2D. And they want to see how close semantically are we getting these things together. And in theory, we want them to be very close, because the whole point is across modalities, we want to see how closely can we get their meaning to be aligned. And on the right side here, without using these tags as anchors, we see in some cases, some things are quite close, but in some cases where I drew these little arrows, they're actually quite far. So for example, person in red with its corresponding text representation in red dots is actually quite far away from each other. And zebra is the same way, where it's quite far from each other in 2D space. But when you use tags in their Oscar pre-training routine, you actually rescue these things together, and they become quite close. And if it's clear, you see zebra is now right next to its image and text, their image and text are right next to each other, and person is also rescued. Other ones are sort of remain the same or average about the same, but these are two pretty clear cases where Oscar actually helped rescue the semantic meaning between these things across modalities. And the final analysis I wanted to highlight in this talk was an ablation analysis, where they said, okay, let's see during learning, what's the difference between inputting no tags, those are the anchors, versus the predicted tags using the convolutional net, or using the ground truth tags from the data set. And the ground truth tags represent something like an upper bound on performance, saying if I know exactly what the objects are in the image, how well can I learn on these things? And something fascinating is that across the board, and I should mention, no tags is sort of a reduction back to the previous visual language model. So basically the just using the words and the visual representations. And so you can see across pretty much these three tasks that they show in this particular figure that you can achieve faster convergence upon the same state-of-the-art performance as before, and then achieve higher performance later on in each epoch or step of the training. And so, for example, we can look at VQA and see without using tags, we can converge upon, say, a dev score around 0.65, around epoch 15, but you can achieve that exact same dev score in 1/3 the amount of time via just including these tags as anchors, and even better if you use the actual ground truth labels. And across the board, the same sort of pattern it remains, and it's quite interesting. So I want to leave with the idea of what does the Oscar pre-trained models actually output, and what does that look like compared to the prior state of the art? And so here's a quick example, or a quick couple of examples, and the main idea is these anchor predictions surpass the prior state of the art. So the first image, you have a train on a sidewalk with people around it, and you have ground truth captions. And in blue highlights, you see what Oscar's included that it should have included, that the baseline model without tags doesn't include. In green highlights indicate what none of the models included in their caption. And yellow just includes what both Oscar and the unanchored version include. So you'll see in the top case, we have this train on the sidewalk, and Oscar inputs or Oscar catches that the train's on a city street and captions it that it's with people nearby, but that's something that without anchoring, we didn't get. And on the bottom case with the red rose and a bouquet with white flowers in a vase, Oscar actually includes that you get it's a red rose and not just a red flower. And so while it certainly doesn't get everything and it's not perfect, it's definitely an improvement over the prior state of the art. It's quite fascinating, and if you found any of this pretty interesting, I'd encourage you to read or listen or watch any of these prior papers and other papers that are related. But that's all I have, and thank you for listening. So, do you have any questions?
Thanks, Sameer. That was great.